So thank you very much to the organizers for organizing this really great workshop, which I've found very enjoyable and very useful, interesting. And thank you for including me in the program. So I'd like to talk about the initial value problem for semiclassical gravity, both without and with spontaneous quantum state collapses on Cauchy surfaces. And this is based on a paper which just appeared on the archive a couple of days ago, and it's joint work with Benito Juarez-Aubry, Tonatiuh Miramontes, who will give the next talk, and Daniel Sudarsky, who are all at UNAM in Mexico. So we take as our model of semiclassical gravity the semiclassical Einstein-Klein Gordon system, as shown here, and we're interested in solutions. And of course, a solution to semiclassical gravity consists of two things: a spacetime, mgab, and a state, in this case omega, a state on the field algebra of the quantum field phi, which lives on the spacetime mgab. And we're interested in solutions which are globally hyperbolic, so mg is globally hyperbolic, and which are Hadamard, so omega is to be a Hadamard state. And there's two questions that we want to ask and attempt to answer about this system. First of all, we want to provide this system with an initial value formulation. So we want to answer the question, what classical, okay, for the metric, and quantum for the state, initial data does one need to specify on an initial three surface C, calligraphic C, and what conditions do they need to satisfy for the initial value problem to be well posed? So just for comparison, in the case of the fully classical Einstein-Klein Gordon system, of course, we know what the answer would be to that question. It would be that we need to specify the three metric, the extrinsic curvature, and the Cauchy data phi and pi for the Klein Gordon field, for the in this case classical Klein Gordon field, and provided they satisfy the constraint equations, the zero-I components of the Einstein equations, we know the initial value problem is well posed. Okay, so we want to find out what's the corresponding answer for our semi-classical Einstein-Klein Gordon system. Okay, and the second question we want to discuss is how could we combine semi-classical gravity with spontaneous quantum state collapses, as in what people know as the GRW theory and various other generalizations of that have been put forward over the years and attempted to adapt to relativistic situations and to curved spacetimes. I've mentioned here a few names of people who've been involved with such a project. Okay, and here we'll just assume that such quantum state collapses, and similarly to in the GRW theory, happen on certain Cauchy surfaces which are non-intersecting and which we'll call collapse surfaces, and that these surfaces that will then be separated by what we'll call epochs, where ordinary semiclassical gravity will hold. So as in this picture here. Okay. Okay, now let me say that these two questions naturally go together. So on the one hand, technically, if the initial value problem is well posed, then to integrate forwards from one epoch to the next when we have these collapses, we'll just need a jump rule specifying how the classical, semi-classical gravity data, and this will turn out to be the three metric and the extrinsic curvature, we'll discuss this later, how such data has to jump when a quantum state collapse occurs so as to satisfy the semi-classical constraint equations suited to the next epoch. Okay. On the other hand, physically, it's very interesting to combine semi-classical gravity with GRW type collapses, because plain semi-classical gravity is ruled out, as we all know, by the Page-Gaelka-Schrödinger cat Cavendish experiment. Okay, so you have two heavy masses. Imagine they're in a Schrödinger cat-like superposition of being in these green locations and in these maroon locations, and you ask yourself the question, how would these test masses attached to this torsion bar, how would this torsion bar twist in such an experiment? And according to semiclassical gravity, the torsion bar would see a symmetric gravitational field, so it wouldn't twist. And that obviously is not what actually would happen in this experiment. But arguably, so plain semiclassical gravity without collapses would seem to be ruled out by, as pointed out by Page and Gaelka, by consideration of such an experiment. However, arguably, semiclassical gravity with stochastic quantum state collapses would be consistent with this experiment. Okay, so let me turn to how we answer question 1. Well, as we all know, because of the need for higher derivative counterterms when we renormalize the stress energy tensor, we expect to need to specify classical data consisting of the, and here I use Gaussian normal coordinates adapted to my surface, consisting of the metric, its first time derivative, but also its second and third time derivatives, okay? Together with an initial state, let's call it omega sub c, on the CCR algebra of C, which will in practice be specified by the three initial 2-point functions, omega of phi phi, omega of phi pi, which when the points are distinct is the same thing as omega of phi pi, pi phi, sorry, and omega of pi pi, where now phi and pi are sharp time quantum fields on C satisfying the usual canonical commutation relations. Okay, note that we expect all three of these quantities to be needed, both to determine the state of the surface and also to determine the expectation value of the stress energy tensor on the surface, because the formula for TAB involves time derivatives. Okay. Further, and along with the constraint equations, we expect that we'll need to require that for given such classical data, omega c will satisfy a suitable surface Hadamard condition, which, let's say in a fixed, in the first instance in a fixed curve spacetime, would guarantee that the state omega of the Cauchy development is Hadamard. Okay, and the main technical difficulty of this work that the four of us did was to understand how to define a surface Hadamard condition. And the difficulty here is that the notion of Hadamard as a point depends on the geometry in the neighborhood of that point. And in particular, for a point in our initial surface, it will depend on all the time derivatives of g on that surface, but only g itself and its first three time derivatives will be specified in the initial data, or at least that's the expectation. And how we resolve this will be the topic of the next talk by Tonatiuh Miramontes. Okay, but here, very briefly, to give you the flavor of the solution, let me briefly discuss a simpler problem, namely the scalar Yukawa model in Minkowski space. So here we have a quantum field phi interacting with a classical background field chi in Minkowski space, and chi is coupled back to phi through the expectation value of phi squared, which plays the role, if you will, of these, it is analogous to the stress energy tensor. Don't worry about this mu here, that's just a renormalization constant that's needed to make this theory renormalizable. Okay. And let's simplify also by taking our initial surface to be a flat constant time surface in some Lorentz frame. Okay, now for a state to be Hadamard for this theory, the 2-point function has to take such a form. Sigma is the square of the geodesic distance between our 2 points. And your to say a state is Hadamard means that it can be written in this way, where this W is smooth, okay? And this coefficient V of the logarithmic term has a covariant Taylor expansion in chi, suppressing here I'm suppressing dependence on x and x prime, so all the terms here are just functions of x, except for sigma, which is a function whose derivatives appear right in this bit and this bit, and that's a function of x and x primed. And the problem is that on C, on our surface, V, as you can see from this expansion, depends not just on chi and chi dot, which are the data we expect to need to specify for this problem, but also on chi double dot, chi triple dot, and so on. Okay. However, we can imagine a process where in a first stage, we can use the equation of motion, okay, that's this equation here, 3a, for chi to find chi double dot, okay, because chi double dot can be extracted from this term here in the equation. And then in a second stage, we could use the time derivative of that equation to find chi triple dot, and so on. Okay, now you might think there's a problem here, because in the first stage, the equation of motion involves the expectation value of phi squared, which involves the Hadamard form, and you might think that you're involved in a circularity. Well, actually, in the gravitational case, you are involved in the source of circularity, as Tonatiuh will explain, but that can be resolved. But let's discuss this simpler case here. Just to define omega of phi squared, we can it turns out, as some of you might have anticipated, we can truncate the covariant Taylor expansion of V as its first two terms, and they only depend on chi. So we end up with a formula for chi double dot, provided a certain limit that defines omega of phi squared, and which involves chi, which we already know as I've said, as part of our data, provided that provided this limit exists. Okay. And similarly, in a second stage where we differentiate the equation of motion once with respect to time, we get a formula for chi triple dot, provided a certain limit which involves omega c and now chi dot, it turns out, exists. And we can proceed inductively to find chi with 4 dots, etc., generating lots of conditions that require lots of limits to exist. And then we define a surface Hadamard condition for this model to be the condition that all those limits exist, together with the condition of being Hadamard for all the thus generated chi, chi dot, chi double dot, chi triple dot, etc. Okay. And then we conjecture that given initial classical data, chi, chi dot, and a initial surface Hadamard state for those data, there is a semi-classical solution which agrees with those initial data. I should say all our work results in conjectures, not with theorems. That would be yet another difficult project to prove all these things. But we think we've established reasonableness arguments for all these conjectures. Okay, so after resolving several difficulties, as Tonatiuh Miramontes will discuss in his talk, we can do similar, but with modifications for semi-classical gravity, and obtain a notion of surface Hadamard initial state for given classical initial data. And we then conjecture that if omega c satisfies the surface Hadamard condition for these classical data and also satisfies the constraints, and actually, in a way, you have to solve them together, again, see Tonatiuh's talk, then the initial value problem is well posed for semi-classical gravity for those classical and quantum initial data. Okay. Now, it turns out that the set of all solutions of semi-classical gravity is too big, and we want to restrict it to a smaller set of what we call physical solutions. And this is all to do with those unwanted higher derivative terms that inevitably accompany semi-classical gravity. And for this story, we need to think of solutions as functions of hbar. I won't read out that comment in brackets, you can read it. And let me also note that if we include, no, sorry, I should say this. Okay, and hbar appears in front of the higher derivative terms, those higher derivative terms that I mentioned, and in front of the singular part of the Hadamard subtraction piece. And also note that if we include quasi-free states with non-vanishing one-point functions, which is something we want to do, in other words, coherent states, and more interestingly, if we include states which arise, let's say, in some Hilbert space representation as superpositions of such coherent states, then the expectation value of the stress energy tensor will, if you think about the dependence on h bar, will arise as a sum of a piece of order h bar and a piece of order h bar to the 0, in other words, a piece which doesn't go to 0 as h bar goes to 0, which you might think of as a classical piece, but it's not really classical, because, e.g., for those superpositions of coherent states, it can have pieces in it with a non-trivial dependence on h bar, like this formula here. Okay. You can all see my screen and my cursor as I move it.
Yes, yes, we can see it.
Yeah, because, okay, so then we define a physical solution to be a solution which in any coordinate chart is a jointly smooth function of h bar and coordinates in a neighborhood, so to speak, of h bar equals 0. Okay. And we then conjecture that for a physical solution, we actually only need to specify the initial values, g and g dot, or equivalently g and the extrinsic curvature on our initial surface, and that there's a notion of initial surface Hadamard state just for g and g dot, and g double dot and g triple dot will be determined by that smoothness condition in h bar at h bar equals 0. Okay. Okay, so how much time do I have left, actually?
Well, I don't remember exactly. You had 20 minutes, but we have a bit of delay, so you can keep going for
okay,
a while.
Thank you. Okay, I have 3 more view graphs, 3 more slides. Okay, so let me now turn to question 2, which is how do we do semi-classical gravity with quantum state collapses? And here we encounter this what jumps question that I briefly mentioned, and I'll try and explain better now. So if a spontaneous quantum state collapse happens on a collapsed surface, then we expect that the state, then the state will change, omega will change discontinuously, or jump, say, from omega minus to omega plus. So the right-hand side of the semi-classical constraint equations will jump. And therefore, to keep satisfying the constraint equations, some part of the classical initial data, G and K, we're dealing now with physical solutions, must jump too. Okay, so how do we deal with that? Well, a simple analogy is semi-classical electrodynamics. So I've just written here Maxwell's equations, but we're to imagine that the charge density and the current arise as expectation values in some state for some quantum charge scalar field, let's say, which I haven't bothered to write down the equation for. Okay, and in this theory, if on a collapsed surface, let's say we have omega minus from the previous epoch jumps to omega plus, determining the state in the next epoch, then the electric field cannot be continuous, because by the Gauss constraint, that was the first of our Maxwell equations, we must have that div E is 4 pi omega expectation omega minus of rho before the collapse, and it's 4 pi expectation omega plus of rho after the collapse. So some part of the electric field has to jump, of the classical electric field has to jump, and a natural prescription is that on a collapsed surface, the magnetic field is continuous, while if we do a Helmholtz decomposition of the electric field before and after the collapse, so I write E plus or minus is minus grad of some scalar plus some vector, which I happen to call q, but it's nothing to do with charge, sorry, which has 0 divergence. So the natural prescription is that q plus is q minus, while this scalar part of scalar that's living here satisfies Poisson's equation with omega plus or minus of rho. Okay, so that has to jump. Okay, this is equivalent to saying that in Coulomb gauge, the electrical potential phi jumps, so that phi plus or minus is the Coulomb potential for omega plus or minus of rho, while the magnetic vector potential is continuous. Okay. Well, to cut a long story short, returning to semi-classical gravity with quantum state collapses on Cauchy surfaces, okay, now everything's curved, of course. It seems that a natural counterpart to this prescription, again for a physical solution, is that the metric remains continuous, and also the transverse traceless part of Kij, the extrinsic curvature, which has two independent components, remains continuous, and that what jumps are the remaining four free components of Kij, which nicely matches the number of constraint equations, right? In electromagnetism, we had one scalar field that jumped and we only had one constraint equation. In gravity, we have four constraint equations, and we have four pieces of Kij that we argue should jump. And we argue that this should determine the new classical data uniquely, so we can uniquely continue Cauchy evolving into the next epoch. Okay, that's basically what I had to say. I realize it's a lot very fast, but hopefully it will serve to advertise our paper on the archive and encourage you to read it and maybe serve as a guide to reading it. Okay, let me mention, to end the talk, one last thing which I think is interesting, which came out of this research, and that is the notion, which as far as I understand is new to our paper, of semiclassical gravity to order h bar to the 0. By the way, semiclassical gravity to order h bar would also be interesting, but and is discussed in the paper, but I don't have time to discuss that. But let me say a few words about semiclassical gravity to order h bar to the 0. So as I said, perhaps one of the most interesting things, I think, to come out of this study as a byproduct is that there seems to be a nice approximate theory that we call semiclassical gravity to order h bar. And like classical general relativity, this is free from the need to add higher derivative terms and free from the need to do Hadamard subtractions. Nevertheless, because of those terms that go like a e to the b over h bar that I mentioned earlier for our superpositions of coherent states, it is a distinct theory from classical general relativity. And we conjecture, so I would encourage you to read conjecture 13 in our paper, that this theory has a good initial value formulation, which is similar to, and no more difficult than, but not quite the same as that for general relativity. Okay, and I'll end there.
Okay, so thank you very much for your very interesting talk. We have a lot of clapping hands, and we have one question from Dan Jansen. Okay. So whenever you want.
Hi, Bernard. First of all, nice talk. I had a couple of questions actually. Maybe some of them might also be answered in the next talk, but before I forget them, I would like to ask them. So you mentioned this Page-Gardner experiment. I mean, yes. I may be wrong, but as far as I recall, this was a sort of proposed experiment, but never actually carried out.
Well, actually, if you read the paper, they say that they actually did carry it out.
Okay.
In a laboratory. But and it's rather amusing the way they carry it out, because the actual measurement has to do with somebody taking a piece of paper into a room and writing down a result that they see on a...
But I mean, I think, isn't it very, as far as I recall, like doing a Cavendish experiment on this scale and having a stable superposition that would somehow lead to something measurable would be technologically very difficult.
Apparently they did it.
Okay. Yeah, the reason I asked is because
Einstein himself did it. Well, and Gaulke. Maybe Gaulke was an experimentalist. I never thought about that.
The reason I asked because a few years ago I heard the talk by people who are planning to do just such an experiment, but we're still running into technical difficulties. So, but maybe Gaulke already found a way to solve it. Then I should look at that in more detail.
As far as I recall, if you read their paper, they claim to have actually done it.
Okay, then I will do just that. Then another question. You mentioned these singling out physical solutions.
Yes.
I assume this is maybe you mentioned this, but I just misheard. I assume this is to rule out runaway solutions, right?
yeah, if you were interested in the late time behavior of semiclassical gravity, then asking for smoothness in hbar would rule out runaway solutions. And this actually, I should say this, and we say it in the paper, this whole idea is inspired by the work of Parker and particularly, what's his name? Jonathan Z. Simon, from about 1993, if I remember rightly. But of course, here we're not using it to rule out runaway solutions, but we're using it to, in terms of, you know, short time behavior. So to not have to deal with specifying the second and third derivatives of the metric off our Cauchy surface.
I see. And the last question I had, is there still time for that? Otherwise, I'm happy to ask it at some later point. But
well, I think you can ask.
Okay, so just to clarify my understanding of what you said about these collapsing scenarios, so collapse of a state. You mentioned because I mean, of course, the paper on this is just out as far as I understand. So
yes.
I can't say I've read it, but am I right in saying that, for instance, what I always thought, well, collapse and semiclassical gravity don't go well together because your stress energy tensor won't be conserved in some collapse.
That's absolutely right, and that's also pointed out, well, in many places, but in particular back in that page. Oh yeah, I've got the date for that page, Gal, paper there. Yeah, 1981 even. Yes, even earlier than I.
But you say if you have collapse, you can somehow use those constraints. So I guess also conservation of let's say the total stress tensor to fix how your initial data should.
Well, the stress energy tensor won't be conserved. It doesn't even make sense to talk about what it would mean, you know, for it to be conserved on a collapsed surface. But the point is that we nevertheless get or conjecture at least, or by putting together several conjectures that we argue are reasonable, that we get a well-defined time evolution from one epoch to the next. Okay, so we get a well-defined way of evolving Cauchy data through a collapse surface.
But at the collapse condition. But at the collapse surface itself, then the semiclassical Einstein equations.
At the collapse surface itself, the semiclassical Einstein equations don't make sense. No. But that's not really so troubling, because after all, lots of things don't make sense at the moment of quantum mechanical state collapse, right? Like in non-relativistic quantum mechanics, the Schrödinger equation has to be suspended at those times.
Yeah, fair enough. Yeah, thank you.
Okay. Well, there is another question in the chat. I'm going to read it, but I think you partially answered it. The question is, when considering a higher derivative equation describing the back reaction of particles to be created in the time evolution, generically, we will get some non-physical solutions showing catastrophic behaviors. In that case, we need to tune the initial conditions so that such conditions are removed. Are you considering similar problems in setting initial conditions? How to treat it?
Yes, yeah, well, there is an interesting point made by Parker and Simon in their paper back in whenever it was, maybe 1993, that for physically, probably what we should really be interested in is not exact semiclassical gravity, but semiclassical gravity just to order h-bar, because after all, we only expect these equations to be an approximation to some full quantum gravity theory, and we don't know what that theory is yet, but it will presumably have corrections which are unknown to us at order h-bar squared. So anyway, we shouldn't believe semiclassical gravity beyond order h-bar. Okay, and if you, as Parker and Simon explained, if you work to order, and we if you read our paper, we'll also discuss this. And if you work to order h-bar, then you don't encounter these runaway solutions.
Okay.
You can look for solutions to order h-bar which don't have runaways.
Okay.